Hello and welcome to Water Quality. In this video, I'm going to show you an example demonstrating complexation. And the example I have here is copper, which can complex with ammonia and hydroxide. So in the first reaction I have here, copper is reacting with ammonia and forming a complex. And we have an equilibrium constant that's given as 10 to the fourth. And in this kind of area of complexation, often the equilibrium constant is described as a stability constant, but it acts just the same as a normal equilibrium constant. Okay, so we're given that the copper ion concentration is equal to the ammonia concentration, and that is 10 to the minus 5 molar. So we want to know what's the complex concentration, so we can use the equilibrium equation. So we have 10 to the fourth, and this is the products, copper ammonia complex over the reactants, ammonia times free copper. And we're going to solve for the copper ammonia complex. And so this is 10 to the fourth times 10 to the minus 5 times 10 to the minus 5, or 10 to the minus 6 moles per liter. Okay, so that's our copper ammonia complex. But copper can also complex with hydroxide, and it can form multiple complexes, but we're only going to consider one here, and that is where copper reacts with a single hydroxide. Okay, so we have a K value of 10 to the 8th, and you can notice that the stability constant is higher than the one up above. And so let's go ahead and solve that. And here we're given that the pH is equal to 8. Okay, so I'm going to solve this over here so we can see the answer from the previous problem. So K is 10 to the 8th, which is equal to copper hydroxide complex over hydroxide and copper. And we're solving for the copper hydroxide complex, which is 10 to the 8th times 10 to the minus 6 times 10 to the minus 5. And this gives us a value of 10 to the minus 3, which is higher than 10 to the minus 6 for the copper ammonia complex. So you can see that the higher concentration is with the copper hydroxide complex. So we can put this is greater than our copper ammonia complex. Okay, so it suggests that this K value, or stability constant, is going to tell us which one is favored, which is partially true, although in this case, because hydroxide is in this reaction, it's very pH dependent. So just be aware that it's not just the stability constant that's going to tell you how probable the complex or how dominant the complex is. It's also pH dependent often, because hydroxide often reacts with metals. Okay, so we've got one more thing to solve, and that is, what is the total copper concentration? So a lot of times students struggle with the idea of the CT, or what does that mean? And it's basically the idea that we're accounting for all of the places where copper can be in this problem. So copper can be present as free copper ion. It can also be present as the copper ammonia complex. And then it can also be present in this problem as the copper hydroxide complex. So the sum of those three things will give us the total copper concentration. And so here we have 10 to the minus 5 plus 10 to the minus 6 plus 10 to the minus 3 this gives us 0.001011 molar. And that is our total copper concentration.